Hi everyone, welcome to our webinar today on pH data logging best practices. Thanks for joining us. I am very excited to be able to share this information with you and look forward to your participation in the webinar. So let's go ahead and just get right into it so we can save ourselves from going over the hour that we have. Okay. So first, I'd like to cover some webinar logistics. The webinar is slated to be 1 hour, and it is being recorded, which means it'll be made available to everyone who is attending. If you can't hear me, please send a message to me in the chat section or in the questions section. I'll be looking at both throughout to be able to answer your questions if I can. And also, maybe it's possible that you aren't hearing me because you are either muted or you haven't called in. So I'm going to take a second to let you guys do that. And if anyone's having an issue hearing me, please let me know. Okay, looks like everyone can hear me. So I just wanted to give you a little bit of a background about myself. My name is Inslee. I'm the product marketing specialist for water here at Onset Computer. And I have a very long history of experience in the marine environment, both personally while I grew up and also academically as well as in my career. So I first started my professional career as an intern at the Moat Marine Aquarium in Sarasota, Florida, working on tagging and releasing sharks for the Center for Shark Research. And then I went to work for Florida Fish and Wildlife Conservation Commission doing NMFS, National Marine Fisheries Survey, fisheries dependent monitoring surveys, where I went out and interviewed fishermen about their habits and what they were finding. And then I went to the University of Rhode Island and received my master's degree in developmental shark biology, which was really developmental sensory biology of elasmobranchs. Since then, I went to the evil side and I started working in the water quality industry as an applications engineer at Hanna Instruments. Then I moved up and did some sales and some global sales management. And now I'm here at Onset. I've been here for 2 years. I love it. I'm enjoying every minute of it. It's allowing me to get out in the field and to really get in touch with the customers. So I love hearing from you all. If you ever have any questions or if you ever have any ideas for us, definitely reach out. We love hearing from our customers. Okay, we are about to dive deep right into pH. I say deep, but it's really going to be sort of like the shallow, middle, deep end of the deep end because we only have an hour. So this is not an extensive, exhaustive chemistry class. And I am very excited to go through this, but I just want you to know I'm going to breeze through some things. I'm also going to touch on some of the basics parts of pH, no pun intended. So we are going to start with water and its properties, since pH is an aqueous measurement. And we are also going to discuss general pH theory, the different measurement methods, as well as specifically potentiometry, which is what this webinar is going to be covering is potentiometry. Maintenance and calibration and cleaning for pH electrodes, and deployment tips. So mostly this webinar's goal is to remain agnostic of who you're using in terms of pH meter, pH probe, pH data logger. A lot of the questions I received ahead of time were very specific about our pH data logger, and I am happy to answer those questions, but for the sake of time, I will likely reach out to each of you individually with answers. But if you have any questions that are relevant to what I'm discussing in terms of general best practices, then please feel free to ask them in the questions box if you think of them, and I'll try to answer as we go. So let's get started. We'll start with water and its properties, and we're actually going to really start with a poll. So this will help me understand what is everyone's background in terms of pH, so that I know how quickly to cover some of the theory and how much of the theory I should cover. So what would you say is your level of knowledge regarding pH theory. If you could select your choices, beginner, intermediate, or expert. Beginner, I'd say, has little to no experience. Intermediate has some experience, and experts like you practically have a PhD specifically in pH, which would be really cool to talk to. I'm going to give you a couple more seconds to finish that poll. In the meantime, let's see. Almost everyone has voted. Try to take like maybe 5 more seconds. Okay. So here we go. Let's share the results with that. The majority of you say you have intermediate, some experience, which means the next couple of slides that I have might be a little bit of a review, but I always argue it's good to review the basics just to make sure that we're all on the same page. We do have some beginners, and that's great. I'm super excited that you're here because I think that I have some useful tips and tricks that you might enjoy learning. And then, of course, we have the experts, and I hope that they are ready and willing to correct me if I slip and say anything wrong. Be gentle. Okay, here we go. So, water and its properties. What we're covering is water an acid or a base? Its neutral charge and when it has a specifically neutral charge. And then why do we even care in terms of pH? I've already sort of answered that with saying that pH is an aqueous measurement, but there's more to it than that. So here we have a drop of water. It's a lovely little drop of water. And the whole world knows that a drop of water, or a lot of people know that the drop of water really is H2O. If you ask somebody what is water, it's not just water. If you abbreviate it or something like that, they'll say it's H2O. So H2O is actually the chemical makeup of the molecules that make up water. And so if you have a beaker full of water, you actually have a beaker full of H2O. But there's more to it than that, of course, because chemistry. So here we have our H2O molecule. We have one oxygen, two hydrogens, and the hydrogens have a positive charge and the oxygen has two negative charge. So we have a water molecule with hydrogen ions and an oxygen ion. In our water, we have H2O, but the H2O isn't always just H2O. It's actually a really cool, fun thing to envision because what it is actually hydrogen ions separated from hydroxyl ions. And then occasionally those hydroxyl ions find a spare hydrogen ion and make water again. And sometimes the H2O finds another hydrogen ion and you have hydronium. And so the thing with this is that it's really showing that water is this dynamic fluid. It is constantly, these things happen instantaneously. Hydronium hardly ever exists longer than a teensy tiny millisecond or way less than that. And it just bounces around. So what we really have is we've got water bouncing around and the molecules jumping together. And sometimes you have H2O, sometimes you have H, sometimes you have OH, and sometimes you have hydronium. So you just have to envision water as this crazy, excited bowl of molecules. But then why do we care? What is an acid and a base? So acids dissociate in water to form hydrogen ions. This is basically hydrochloric acid. We have our chloride and we have our hydrogen, one of each. And when you put hydrochloric acid into water, it separates out to, and this isn't permanent, this is a constantly moving, this actually should have another arrow on the other end, but it separates out into chloride and hydrogen ions. So what we're seeing is that this is a spare hydrogen ion that the hydrochloric acid is capable of donating essentially to the solution. Okay, so bases do the opposite. When a base dissociates in water, it forms hydroxyl ions. So here we have sodium hydroxide. Sodium's a rather big ion. And then we have the hydroxyl molecule. And again, this should have an arrow on this end. But when you put sodium hydroxide into water, it dissociates into sodium, a very positive or a positive ion, and hydroxide. So as you can see, this is a base because it dissociates and donates a hydroxyl ion to the solution. Okay. So, sorry, this is, okay. So here we have sodium chloride, which is like table salt. And when you have table salt, you add it to water and it dissolves rather quickly unless it's saturated. And you end up with sodium and chloride. So one would beg to differ, you know, is salt an acid or a base? Well, it turns out that it is neither, because it is neither donating a hydrogen ion nor is it donating a hydroxyl ion. So salt may dissociate like hydrochloric acid or like sodium hydroxide, but that does not make it an acid or a base. Okay, so then taking that a little bit further, and I hope I'm not going too quickly with this. I know it's very basic for some people. The question then is water an acid or a base? So here we have a beaker of water, and we have some water molecules, some hydroxyl ions, some hydrogen ions, some oxygen ion just randomly sitting there. And so if we take a look at our water molecule and we put water in water, it ends up becoming a hydrogen ion and a hydroxyl ion at some point in the life of the molecule. So it's an acid, right? Because it donates a hydrogen ion and it donates that to the solution, and it's perfectly classic acid. But at the same time, it's a base. And it's rather interesting because it also donates a hydroxyl ion to the solution. So this was kind of a trick question where water is actually an acid and a base. Are there any questions so far about that? I recognize that we have varying experiences here, and it's totally fine to ask any questions that you may have. Just pop them into that question box and I will keep an eye out on them. Okay, let's move on. So now we're going to discuss the neutral charge of water very quickly. Now that we've learned that water isn't just a beaker full of H2Os, it's a beaker full of H's, OH's, H2Os, and H3Os, and constantly moving around and binding and unbinding. So pure water and its properties. One of the main properties of pure water or the essential property of pure water is that it has a neutral charge. Here's our water molecule again, H2O, means we have two H's, one oxygen with a -2 charge. It's a neutral, no charge molecule. But then we have positive ions and negative ions, and they just happen to be in equal amounts, and that makes it have no charge. The two positives are neutralized essentially by the two negatives. But why are we saying particularly pure water? Because if you look at pure water, H2O, it'll split into its hydrogen ions and its hydroxyl ions. So whereas on the last slide, we were showing how water molecules are neutral, we're showing here that not only are water molecules neutral, but when they separate, they will always separate to a positive and a negative charge, which means that water as a whole is always neutral when it's pure, absolutely pure room temperature water. And what this also means is that we have equal concentrations of hydrogen and hydroxyl ions. And this is really important, one, because it does show that water should be neutral. It should have zero charge if it's pure. And two, it relates the hydrogen ion concentration to the hydroxyl ion concentration. And for those of you who are familiar with pH, you actually have an idea now where we're going with this. So why do we care? Why do we care about all these properties of water and the hydroxyl ions and the hydrogen ions? What does it have to do with pH? So let's talk about pH theory. And again, this is a brief review of the pH theory. You do want maybe a more in-depth review, and if you're looking for that, then that would be a longer webinar. But hopefully, we'll have a white paper out for you soon, discussing in more depth the pH measurements. Okay, we're back to our buddy, the hydrochloric acid ion or salt. We put hydrochloric acid in water, and we get chloride and hydrogen. It is an acid because it donates that hydrogen ion to the solution. And so here we're going to start with our definition of pH. pH is the power of hydrogen. There are some differing conversations about what that P stands for, the potential of hydrogen, the power of hydrogen, potentii, hydrogenii. But in the end, the bottom line is it is the concentration of hydrogen ions in an aqueous solution. So here we have our water, and we have hydrogen ions sitting there. How many hydrogen ions per volume do we have? That's what pH is telling us. So if we threw in hydrochloric acid, you can see that since the hydrochloric acid dissociates readily, it is also going to show the, I don't know why my mouse won't work. It's also going to show it's also going to dissociate into adding more hydrogen ions to it. Sorry about that. Okay. So we added these 3 hydrogen ions. And to calculate this, one classic algorithm for what pH is, and this is the most simplified version that you'll have, is that pH is the negative log of the hydrogen ion concentration. Really quickly, classically speaking, the negative log of the hydrogen ion concentration was actually meant to be the negative log of the hydrogen ion's activity. And as it turns out, the activity is equivalent to the concentration for hydrogen. So modern, I guess, ways of discussing it are to say negative log of the hydrogen ion concentration. Okay, I hope I still have you, and I hope you're not glazing over yet, because we're going to get into some fun stuff in a bit. This is the pH scale. As I said, it's a logarithmic scale. So what that means is that, for instance, at pH 7, which we know would be pure water, the range for it, we call the pH 7 range neutral. And that means that we have point and then 6 zeros, 1 hydrogen ion concentration. So it's 0.000001 when you have a pH 7. And then as we get more acidic, we are obviously adding more hydrogen on by decade. So jumping from pH 7 to pH 6 takes us a decade higher in the concentration. So it's a little bit confusing to some people that a high pH means acidic, because most people think acidic should have a higher pH value, but it's actually the inverse of that. So when someone says to you, well, it's just a pH change from 8 to 6, that's 100 times different. So just keep in mind, this is a logarithmic scale, and just because it looks like it's a 1 unit change, it's actually a significant amount. Okay, so back to our definition of pH. It is based on water. So it's based on this relationship of water dissociating into hydrogen ions and hydroxyl ions and then reforming water molecules. So that's why there are the 2 arrows here, as they should be. Pure water, to review, has the same concentration of hydrogen ions as hydroxyl ions. And it just so happens that in pure water, that means there are 10 to the minus 7 molar hydroxyl ions as well as hydrogen ions in pure water. And that 10 to the minus 7 means 7 pH, since we know that pH is the negative log of the hydrogen ion concentration. Are there any questions so far on that? Okay, great. So the main thing that we're going to focus on is concentration of hydrogen ions in an aqueous solution. And one note to remember, kind of a note bene, is the difference between alkalinity and acidity versus acid or base. So alkalinity and acidity describe the ability of a solution to resist a change in pH in response to either the addition of an acid or a base. So when you have a base and you're adding an acid to it, how quickly the pH changes is described as alkalinity. When you have a when you have an acid and you're adding a base to it, how quickly it changes is acidity. The alkalinity and acidity of a solution cannot be determined using just a pH measurement, because pH only indicates if a solution is an acid or a base. pH is used through titration to determine whether that solution is what the alkalinity is and what the acidity is of a solution. Okay, here we are. We are at our next poll. Which method do you currently use to monitor the pH of your system? The options here are litmus paper, indicator strips, photometry, or a handheld pH meter, or maybe you grab samples for laboratory analysis that you take back to the lab. That one's a bit tedious, so I'm not surprised there aren't that many people that do it. Maybe you've found yourself to our new pH data logger, the MX2501, and maybe you're currently using a multi-parameter sonde for data logging. Just going to give you like 20 more seconds to vote so we can continue on. Okay, interesting. Looks like a lot of you are using the handheld pH meter, and I assume that means that you're sending someone out there at regular intervals to drop in a pH electrode and read the data. That's pretty much the most popular one. Okay, so I'm going to close this poll, and let's see. Let's move on. So here we have, I'm just going to briefly discuss, very briefly, what the other options are aside from potentiometry. Here I'm showing litmus paper and indicator strips. So here's your litmus paper, classic bench chem, piece of paper that responds to an acid or a base by changing color. And then we also have plastic pH indicator strips. They are different. One changes color and it's sort of very, very objective, I would say. And indicator strips, you take a stick and you dip it in your sample, and whatever color this changes will actually help you understand the pH to a 1 unit degree of pH. So you'll see if it's like 1, 2, maybe it's an 8, but you don't know exactly what it is. So these are generally very low resolution, low accuracy. You're not figuring out to the 100th degree what the pH is. Then there are the test kits. They're like mini titrations. You put your sample in here and then you add in the drops and let it react, and then read the scale that's on the side of it. This is like what people use for pools and for hot tubs, fish tanks, all sorts of things where, you know, knowing to the 0.00 degree isn't necessary. This can be adopted essentially to become red. Instead of your eye looking at this, you use a photometer and you are able to do the same thing, drop some drops in, put it into the photometer, and the photometer will tell you what the pH is. Again, this this could have better accuracy than all the three at the bottom here. The only thing is that with photometry, the color of your sample will affect the reading, and the turbulence or any interfering ions or chemicals in your sample will prevent the reaction from occurring. So this is another one that if you're not looking for consistent accuracy, maybe that's what you're going to use. Okay, so potentiometric, this is the method that I'm going to cover. It is the most common method out there for scientists and educators, aside from ISFET, and ISFET I'm not going to cover either. That's a technique for monitoring pH as well in a somewhat potentiometric way. It's just a little bit of a different method, has different advantages and so on. Okay, so potentiometry uses the measurement of the voltage that's generated by an electrochemical cell at 0. So the potential that's generated is usually proportional to the thermodynamic activity of the ion that's being measured. In our case for pH, this is hydrogen. And electrode cell potentials and the hydrogen ion activity are then related using the Nernst equation. So this guy Nernst made this equation. It's actually not just used for pH, it's used for other ions in terms of like ion selective electrodes. But basically it comes down to this calculation where you have an observed potential and your reference potential, which should be stable. It should not be changing. That's why it's a reference. And then again, the logarithmic values are coming in here. So you have ln, sorry, this should be a base 10. And then a couple of constants like the gas constant, Faraday's constant, the valency of the ion being measured, which happens to be 1 because it's hydrogen, and then temperature in Kelvin. And then again, this is meant to be the activity of the hydrogen ion, but really in our case, we're just talking about it as the concentration. Okay, so potentiometric method here, we are monitoring how acids dissociate into water and release a positive ion, or how bases dissociate in water and release negative charges. In a very general sense, you can see that a potentiometric pH meter is going to be very similar to a multimeter, or voltmeter or voltimeter. So multimeters have a sensing plug and the sensor. You've got the COM or the ground port. You have your multimeter, that's the meter essentially, and then the battery, which is your sample. So if you look at a pH meter, you have a sensing electrode, a reference electrode that currently a lot of electrodes, pH electrodes, have combination of the reference and the sensing electrodes. You have your meter and your sample, and then temperature. Temperature is a key ingredient in measuring pH. And again, this electrode, for instance, has the temperature integrated inside of the electrode. So I know that this is all a lot of theory that I'm throwing at you, but to be able to understand where we're going in terms of best practices for maintenance and for calibration and so on, it's really important that you understand this information at a basic level, just because it'll make more sense when I explain things later on. So the pH electrode and meter and so on comprise one whole system of cell potentials. And you have basically 9 different cell potentials in your electrode as well as in your sample. And then the 10th would be your meter's internal electronics, essentially, that would be adding to the potential. So when the pH meter takes a potential reading, it is reading the potential, the added total potential of all of these, your sensing wire, your sensing buffer solution, your inner hydrated layer, glass layer, outer hydrated layer, which make up your glass bulb, the sample, the reference junction, the reference fill solution, and the reference wire. So the glass bulb, these are the two key things here in terms of maintenance and calibration that I'd like you to take heed of. The glass bulb itself is composed of 3 layers. It sounds kind of crazy because everyone thinks, oh, it's just a glass bulb. But really what you have here is, if you have your electrode properly conditioned, your electrode should have a very nice microscopic layer that you can't see. So yes, you do just see glass. And this layer here, it's either called the gel layer or the outer hydrated layer. Either way, this layer is a very critical component of the electrode. And because this layer is so important, it's really, really important, for instance, when you're maintaining your logger, that you don't touch the glass bulb without recalibrating afterwards. Or if you're storing your electrode, that you don't dehydrate it by storing it in, for instance, distilled water. So some of these things affect the outer and the inner gel layers, and then that'll affect how the pH-sensitive glass, which is this black line here, interacts with the ions that are in its buffer solution, internal solutions, and the sample. And the other very important potential here is the junction. So your junction can be made up of several different styles of, there are several different styles of junctions. There's a single ceramic like this one, or a double junction, or an annular junction where it goes around. So if you have our pH logger, that's what our pH, ours has the fabric junction. So there's a fabric junction, there's a ceramic for it. So there are all different styles of these junctions, but in the end, the most important part about the junction is that it creates essentially a circuit or a connection between your reference wire, which is hopefully stable, and the sample, and then again through the porous hydrogen sensitive glass to your sensing wire. So you've got a basically closed circuit, and that reference junction is crucial in terms of the measurements as well. So you want to make sure that that's clean and that you maintain your junction just as well as you maintain your electrode, for instance. And we'll cover that in a little while. So here's our glass bulb. It has 5 different potentials. Then the junction has 1, 2, 3 in terms of how it relates to the reference. Sorry about that. So if you're going to take one thing from this slide in terms of best practices, I would strongly suggest that you remember that the glass bulb isn't just meant to be cleaned, but it needs to be hydrated and conditioned, and we'll cover this again. And the reference junction as well, same thing. You don't want a dry reference, especially if it's a ceramic, and you also don't want a dirty one. Okay, now we're finished with theory, essentially. I mean, we're going to touch back on what we've discussed, but we are now going to discuss how to maintain the electrode properly. This is probably why you're all here. And again, I just want to make sure that you understand that this is about any pH logger, even if you have a multi-parameter sonde, not our MX2501. These are important things to consider for everything. Every manufacturer's pH, potentiometric pH meters. So why do we calibrate a pH electrode? Well, we do this because you need to compensate for any manufacturing tolerances. Some pH electrodes are hand blown, and when you have a hand blown anything, you're going to have variances from one bulb to the next bulb, and it's important to compensate for those tolerances. And these tolerances are usually expressed by the manufacturers, so you'll know what to expect from your electrode, but they also are pretty standard tolerances that you need to compensate for. In addition to which, you want to compensate for electrode aging. A brand new pH electrode is wonderful because it's shiny new. Hopefully it's conditioned and your outer gel layer is nice and hydrated, as is your inner gel layer. You don't have any cracks. But as you use a pH electrode, that glass, which is hydrogen sensitive, will start to sort of break down, I guess you can say, because it is a silica glass, and it will age. And so as that happens, you want to compensate for that aging by calibrating. Okay. pH calibration requires specific pH buffer solutions, and it depends on the manufacturer. So these buffer solutions have known values, and they're meant to create a linear graph of the electrode's response. And so this graph will be potential versus pH unit. Depending on the manufacturer of your meter or your logger or your sonde, you'll have hopefully at a minimum 2 pH buffer solutions recommended by the manufacturer, and maybe 3, and there are 3 standard ones that a lot of people use. That's 4, 7, and 10. But for different applications, you might require different calibration buffers, so you'll want to make sure that you are using the correct buffers. And we'll talk about that in a little bit. But if anything, the buffers should bracket the pH value of your sample. So for instance, if you're measuring the pH in the ocean tends to be around 8, very generally around 8. So I would recommend calibrating between 7 and 10 at a minimum. And you always want to calibrate to 2 points, because it will create 2 correction factors. And in order to get both the offset and the slope, you'll need to calibrate to more than 1 point. Okay, so let's start with the offset. When you calibrate, for instance, this person actually calibrated, apparently measured, calibrated at 4, 5, 6, 7, 8, 9, and 10. But let's just pretend, for the sake of pretending, that this person calibrated at 7, 4, and 10. And our offset is defined as the potential, the millivolt reading, at pH 7. So here we go, we have our offset. Theoretically, you want your offset to be 0 millivolts. You want your pH electrode, excuse me, at room temperature to be, you want it to be neutral, actually 0. And then if you have your potential for your offset plus or minus 30 millivolts, if it's within that, then that's an acceptable range. But anything outside of that, I would recommend either cleaning your electrode or starting the calibration over. Okay. Any questions about your offset? Okay. Sorry. There we go. Okay, so the second correction factor that we get when we calibrate, and hopefully you get because you're doing more than 1 point, is your slope. And the slope is the change in the potential between at least 2 buffer solutions. And again, we're pretending here that this was done at 7, 4, and 10. It is expressed as millivolts per pH and reported as a percentage of the ideal slope. So if you can remember back to that Nernst equation, that crazy equation that looks at potentials and constants and gas constants and so on, you'll remember that, or sorry, you'll note that at pH 7, at room temperature, the slope of the calibration curve will be negative 59.16. And so any slope that we get after that when we're calibrating, because the slope will change, we take that value and divide it by negative 59.16 at 25 degrees C. And the acceptable range for that is between 85% and 105%. I would argue, now that we know what offset and slope are, that if you're about to deploy, for instance, a pH logger or a multi-parameter sonde for a long deployment, 6 weeks, 4 weeks, if you're hovering near 85% and an offset that's close to plus or minus 30 millivolts, my recommendation would be to get a new electrode prior to the deployment, just for the sake of making sure that the electrode doesn't drift too far outside of acceptable ranges while while it's deployed. So if you have a bad slope, I forgot to mention this, it's important to check the buffers that you have and try calibrating again. So here is a fun graph of a couple different calibrations that I put together. And it's meant to explain further how slope and offset can affect your readings. So in blue, which is where the arrow is pointing, we have an ideal electrode, an ideal buffers actually. The slope is, oops, sorry, that should be a negative 59.16, but it's a negative 59.16 slope, which means 100%, and the offset is 0. And if we continue looking at the other calibration, this green calibration here, which is where the arrow is pointing, the slope is out of range, but the offset is fine. So we see a lovely offset right through 0, which is delicious, but our slope is crazy steep. This means your buffers might be contaminated or your electrode might be replacing. My recommendations whenever you have either a slope or an offset that are off, the first step should always be for you to do a visual inspection of the electrode to make sure there are no cracks, as well as to look to see if your electrode needs cleaning, and go ahead and try giving it a clean, or try cleaning it and then reconditioning it before trying your calibration again, because that might just be the problem. And I'll talk about that in a little bit. Here we have the slope that's fine. It's actually perfect. It's perpendicular to the perfect electrode. And but the offset is way out of range. It's negative 50 millivolts. So this definitely needs cleaning or reconditioning. And it's also possible that it's cracked, because in the end, potentiometric readings or potentiometric electrodes will always read a potential even if it's cracked, even if there isn't electrode attached. So something to keep in mind with any product that you're using is to also check the connection between your electrode and your either meter or logger, because, and it's fun to experiment with this in front of customers. You guys should definitely try it if you're having issues or you want to teach your students something fun. Take your pH electrode and detach it from, for instance, the benchtop meter if you're teaching, but still have the cable going back behind the pH meter to the point where no one will notice it unless they meant to look. And what the students will see is that it's actually still reading a potential. So pH is kind of annoying like that, where if your sensor's not working, you're still going to see data. So this is definitely one thing to be aware of. If you don't have a slope, it's possible that your electrode's cracked enough that it's not able to read a different potential. It's reading the same thing no matter what solution you put it into. That may be a crack on your electrode, and it is possible to have micro cracks that you can't even see on your electrode. So be aware of that as well. If you have, excuse me, noise or a slow response, then it's probable that your junction is dirty. And so now we're going back to the bulb dynamics that I discussed, the potentials. Your bulb has the 3 hydrated layers, the 3 layers, including the 2 hydrated layers. And if those are affected in any way, you'll have poor readings during calibration. And if you have any cracks, or if it's dirty, or if your junction is dirty, you're going to have slow readings, slow responses. And for those people who are logging pH, you want an electrode that is clean, because, especially the junction, because if you're logging every minute, for instance, which would be somewhat excessive, but if you're logging every minute, your response time might be longer than that minute. So making sure that electrode stays clean is rather important. Okay, one more poll for you guys. True or false, temperature does not affect pH values? I'm going to let you answer that. This will be a quicker one, I think. Much quicker response. Okay, so the answer is false. Temperature does affect pH, and it is a rather important part of the pH measurement. So it is really, really important that temperature is mitigated or monitored. So pH calibration conditions to consider. Here on the right, we have a graph that shows 4 different pH calibrations. And these 4 different calibrations were performed at different temperatures. So the blue one, which is the solid one with the square points, was done at 25 degrees Celsius. And as you can see, it looks just like my quote unquote ideal electrode where, you know, it's got a beautiful offset, it's got a beautiful slope. Something that's wrong with this is that when you change the temperature, so this triangle one is 100 degrees, this one is 50 degrees, this one is 0 degrees. What you're actually going to see, and so this is somewhat of a misleading graph, is that all of your pH values are going to change. The slopes are different, of course, but your pH 7 value isn't always the same. So when you're calibrating, and I'm going to show what I'm talking about in just a second, but when you're calibrating your electrodes, it's important to calibrate close to what you're expecting your sample to be. If you're mid-deployment and you're out in the field, for instance, maybe you're up in Colorado and you're doing acid mine drainage, you would ideally calibrate your electrode at the same temperature that the water is currently at. To do that, it's not necessarily the same temperature as the air. What it is the same temperature as the solution. So you can either soak your buffers, float them in the water that you're testing just to get them to equilibrate, or you can cool them or heat them. Do not put them on direct heat, but get them close to at least the temperature so that you're seeing the same activity. Calibrations at temperatures that are a lot colder or hotter than 25 degrees C will require extra time. So keep in mind that it is okay to within the tolerances of your manufacturer's electrode, it is okay to calibrate at different temperatures. Just make sure that you're remembering that your pH electrode that was sitting in your car, for instance, on a hot day in Florida, is likely going to have an internal temperature of that electrolyte that's somewhere in, let's say peak summer, it's somewhere in the 90s even, but your water's like 70 degrees. So you'll want to make sure that you give your electrode time to equilibrate to the sample, or that you're also calibrating to the sample's temperature and also letting the electrode equilibrate to the buffer. So why I said that graph was misleading is that if you look here, this is, for instance, our buffer solutions, and on the buffer solutions, and on almost anybody's buffer solutions, well, they should have this, and if they don't, I would strongly recommend that you find one that does, because they're all pretty much the same. But on here you can see Celsius temperatures and Fahrenheit temperatures, and then the pH at these temperatures. So one thing with pH 4 is it's a very stable pH buffer. It maintains value really well. It maintains value at different temperatures really well. As you can see, it's 4.01 and then 4.00 for a lot, and then 4.01. It's only at the high temperatures where you start seeing it changing. Whereas with pH 7, when you see 0 to 45 degrees Celsius, the pH will go from 7.12 through the 7 at 25 degrees and then down to 6.97. So paying attention to what the temperature of your solution is and what the actual pH value should be. This number is usually, and it should be, what's used by the manufacturer to create your slope and your offset. So the answer to the question is definitely pH is important. And one more thing that you can see here is pH 10 buffer from 0 to 45 degrees has a huge variance. I mean, it goes from 10.31 at 0 degrees Celsius to 9.86 at 45. So keeping that in mind, this also is a really good example of how pH 10 buffer has a very low buffering capacity, I know the irony is there, but it is easily contaminated. It will easily change its value. So one good best practice tip that I can give you is that even if you're doing lots of calibrations using pH 10, I would recommend keeping the bottles small, 500 mils, maybe even a liter if you have to. But that way you're not having buffer sitting open for too long and then getting contaminated just by the air. pH 10 will change its apparent pH just with the CO2 that's present in the air over time. So keep that in mind when you're storing your pH buffers. Okay, another thing to consider when you're calibrating, and this is something that was new to me, a customer actually shared this with me, so I'd love to have a discussion with anyone on it if they are interested, but it is important apparently to calibrate your electrode at altitude. Again, going back to, for instance, our acid mine drainage, which is here, the pH logger was deployed in here, and the calibration should be done, I can't remember how many feet up we were at this, maybe like 10,000 feet. I don't know. I might just be making that up, but we calibrated, at sea level, and then we deployed at altitude. And it was actually apparent that it's important to calibrate at altitude as well. Maybe this is a dumb moment for some people, but for me, I'm a ocean person, not a mountain person. So this was an interesting one, and maybe you didn't know this either, and I'm hoping that this is valuable information. When do you calibrate your pH electrode? It's important to calibrate prior to deployment, especially when you have a new pH electrode. It doesn't matter that it's new and it just came in from the manufacturer. It is still important to calibrate that electrode because shipping can cause changes to it. Even just unplugging a BNC pH electrode, and that's the kind where you push it in and turn it, even just unplugging it and plugging it back in, you should actually recalibrate that electrode because the potential can change just by how you plug it in, which is why it's important to calibrate after you replace the electrode. And again, going back to those hydrated gel layers, after you clean or recondition a pH electrode, it is important to calibrate again because you have changed the dynamics of those gel layers. One, from cleaning, you may have stripped them, and that's why it's important after you clean them to recondition them by soaking them in storage solution. But two, also because you may have touched it during the cleaning, and then in that point, you've almost physically removed the gel layer, and you just want to make sure it's there by reconditioning and then calibrating to make sure that you're calibrating for that. How often you calibrate during deployment, if you have a pH logger or multi-parameter sonde, really depends on your application and your environment. So you could be, I have a pH logger deployed right now in the Quashnet River on the Cape, on Cape Cod. And one of the things that I really don't have to do that often now that it's, negative 80 degrees outside is clean it because it is not getting fouled by anything. The only thing it's getting fouled by is potentially some sediment, but that just washes off right when I take off the cap. So it'll really depend on the seasonality of your application as well as where you are and the style of water that you're in. And just because I used to be an applications engineer and now I'm a product marketing manager, it is super, super, super important that you always refer to your user manual for the specific product that you're using for more details on how to properly maintain and store the electrode. Every manufacturer is going to have their different nuances about what they recommend and what they don't recommend. But in the end, if it's a good manufacturer, they will definitely make sure you know the best ways to use your pH electrodes. So it's always important to read the manual. Okay, briefly, because I know I'm running out of time. Cleaning the electrode. Dirty electrodes can result in faulty data. So if you have a dirty glass bulb, for instance, then you may get bad millivolt readings because those dirt spots there are actually adding potentials to the overall potential of the system. And by adding those potentials, you're actually ending up with incorrect readings. You could also have a dirty junction. So here's your junction in this case, and if it's dirty or if it's clogged or even if it's dry and caked with salt, because these are high salt electrolytes inside, you will actually have a slower response time that may be slower than your interval between readings, which then gives you bad readings as well. To clean a pH electrode that you're using specifically for data logging, this is different than lab analysis since it's not presumably sitting too long in your sample. The first thing that you want to double check is that the scale and salt deposits that are on there, maybe from your salty sample, are removed using a dilute acid. You can use dilute hydrochloric acid, or even just vinegar and water, or just vinegar. That'll help basically dissolve those deposits. If for some reason there's oil around your glass bulb, so maybe it got contaminated with maybe you're monitoring in an oil spill, recognizing that pH is pretty much not accurate or repeatable in terms of measurements in non-aqueous solutions. But if there's oil on your glass bulb, then you can remove it with swishing in a mild dishwashing soap, keeping in mind again that this will require reconditioning afterwards. Only if absolutely necessary. If for some reason soaking it in an acid or swishing it in some dishwashing soap doesn't work, only if those don't work, then you may want to consider, and I'm very hesitant to recommend this because I come from the laboratory world, but you may want to consider using an extra soft, think like a toddler toothbrush, to very gently brush the glass bulb. Sometimes it is necessary to do that. If you have to do that and you're doing it with a super, super, super soft brush, then you might be able to get the dirt off, and you might even get the dirt off of the junction, but soaking this in an acid would really help. No matter what, after you've done this, you must condition. And my recommendation, after cleaning it, you should always recondition an electrode. If you've cleaned it with just some acid, then you can recondition it for like 5 or 10 minutes just in storage solution, just to get it that sort of hydrated gel layer, a happier hydrated gel layer back. And that's this layer again. Or if you've done something like dishwashing soap for an extended period of time, or you've brushed it with a toothbrush, or even if you've been logging in fresh water, then I would recommend reconditioning for a minimum of 15 minutes, or maybe even like an hour, and then overnight would be the best option for all of it. If that's the case, if you find yourself having to do that, then your best bet would be to have spare electrodes available when you go out to sort of check on your logger, download the data, maintain the logger itself, the body of the logger. If you have a spare electrode, then you're able to just swap it out with a clean bulb that had been cleaned and reconditioned, and then recalibrate every time. Anytime you recondition your electrode, every time you clean your electrode, you should definitely recalibrate. So this is an important thing to consider when you are buying a pH logger or a multi-parameter sonde, and that is, how expensive are the replacement electrodes? They are meant to be consumables in my eyes, so they shouldn't be too expensive, but for general purpose pH electrode, having an extra on hand is always a good idea. Having 2 extras in case one gets cracked is an even better idea. And that's more about the high maintenance nature of pH electrodes. Okay, we're getting there. A few more slides. Deployment tips. This is a fun one because there's some really fun applications that I've seen people doing and some crazy ones I've seen people doing, and it's all fun. So deployment tips. The pH loggers usually, or loggers, I guess, data loggers, usually have a way of hanging them somehow. So I'm going to go with what I'm very familiar with, and that is our pH data logger. And that's what you see here. But likely any data logger, like a multi-parameter sonde, or maybe a pH data logger that you have, will have very similar attributes. So what we have here is a rebar, my wonderful fake rebar, and a pH logger, with a lanyard hole and a lanyard attaching it to the rebar. So this is a nice way to hang your pH data logger or multi-parameter sondes if you're in water that is calm, so like a lake. So for instance, we have this pH data logger was actually deployed in moving water, for instance. And so what we're finding is that the electrode is being moved rather close to the surface. It may not be submerged if this were a river, for instance. And you just want to make sure that when you deploy your logger, you have your temperature sensor, your glass bulb, and junction submerged throughout the deployment. And then if, for instance, this is being deployed not in a lake that isn't moving, not in sediment, in non or slow moving water, then you'll want to consider using cable ties. So with our pH electrode, we have grooves on it, and this actually allows for the user to mitigate the potential of flow by attaching the logger to the rebar. And it's actually really important to consider deploying it at an angle greater than 15 degrees below horizontal, because if it's not at 15 degrees below horizontal, you could potentially get air bubbles in the glass bulb, and the air bubbles will affect your readings. So another thing to keep an eye on when you're about to redeploy your logger is to make sure that the pH bulb has no air bubbles in it. If you're in turbulent water, if your logger's in turbulent water or water that has debris for some, it'll maybe have branches flowing down it, we recommend that you deploy it in PVC pipe with holes. And here's just one example of a way of doing that with a cinder block. As you can see, this pH logger is attached with the lanyard to the cinder block, but then also put into a PVC pipe that has holes and allows the water to flow through. And then the tie wrap is actually attached to the logger and to the PVC pipe to hold it really well. Between deployments, it's important to store your electrode in a storage solution. If, for instance, you have the copper guard that comes with our pH data logger, or other manufacturers use copper tape and so on, it is important that you don't put that copper in the storage solution, because that storage solution is super salty, and it will react with the copper and can actually cause some damage. For long-term storage, just store the pH electrode outside of your logger, or I would recommend detached at least from the multi-parameter sonde or your logger, and in storage solution. If you're storing it just over like a season, for instance, maybe you're only logging during warm weather and you're storing it from December to March, it's a good idea to keep it in its storage solution, refreshing it occasionally. So that just means going to it, unscrewing the cap, and rinsing the bulb off, rinsing out the cap, putting in new storage solution, and putting that back in, putting the pH probe back into that storage solution. That's the best way to keep it reconditioned and to keep it from potentially dehydrating or getting foul with bacteria and so on. Another option is if you're storing it for an extremely long time, one option I've seen recommended, and I'm not 100% sold on it, but is to store it dry, meaning you just take your electrode out of any storage solution. That was one manufacturer's recommendation, and I'm not sure I would actually recommend that too much, but it is an option, especially if the manufacturer for that electrode says to do it, then by all means, maybe follow that. But that's for like an extended period of time, like several months or the majority of a year. If you store it dry, then it should be okay, and you're saving the electrolyte essentially. But then you'll want to definitely recondition by soaking it in a storage solution for, I would argue, a couple of days before deployment. So that is what I have to cover today. I apologize for going over. I do have some helpful links here for onset products. We have for our MX2501, we do have this awesome website that shows that provides you with videos that I have been working on, how to replace your pH electrode, how to calibrate the MX2501, how to clean the electrode, similar to what I just discussed. Also, how to maintain it. This is coming out soon, so this will be a video that's going to be released soon, and then I'm also working on a white paper. As I discussed, it'll be a more in-depth review of what I've just covered in this webinar. And if there's anything else that you'd like to see, shoot us an email, customer service, or maybe your contact is Becky Fish for the US. Shoot an email to her and say, look, I'd really love to have a video guidance on, and it doesn't have to be the pH electrode, it could be anything. We're really excited by these new how-to videos, so definitely give us some ideas on what else to do. As always, it's important to read the manual. For our current users, definitely look at our user manual for any tips and tricks. Our knowledge base is a really good place to go if you have any questions. And then, of course, you are more than welcome ever to contact us. International customers, we recommend you go here. US customers, feel free to email Becky Fish or even our customer service for questions and concerns. And with that, I am here with the end of our conversation, looking to see if there are any questions. Okay, so it turns out my questions were not refreshing, and you have been sending me questions. So let's see. Someone asked who does pH readings in boiling water. You would be surprised. Turns out the Middle East has a tendency to be monitoring in temperatures of 50 degrees Celsius. So that's where we'll see that. Okay, let's see. Someone asked about a pressure component. There isn't a pressure component. It's the gas. That's probably grabbed up in the gas constant. So that's where I would expect to see in the Nernst equation any effects of pressure. But also temperature plays into that. So the higher the temp, that's why temperature is also important, because you are looking at the thermodynamics of a solution. So pressure does matter, and that's why also altitude will be important too. If your electrode is going to experience two drastically different temperatures within the same experiment, excuse me, should you calibrate them in both temperatures? Good question. Yes, I'd be interested to hear what the two temperatures are. But yes, that would be interesting to see. I haven't heard of anyone doing that myself. So yeah, that's interesting. For a pH probe that's been deployed in wastewater, you could use bleach on it. I would actually rather you used hydrochloric acid. A mild acid wash should work. Also, with wastewater, it's important to use the right electrode in terms of so the electrodes you saw throughout my PowerPoint were glass bulbs. They were the actual bulbs. They're very general purpose pH electrodes, but there are also pH electrodes that are specifically designed for industrial applications, and that would be a more like flat tipped electrode that's easier to clean, has a specific junction. And so if that's the if you're looking for that with our product, something that I am looking into is maybe adding optional pH electrodes that are for different applications. And the more I hear about that, the more I think the business will be likely to support me in that. Someone asked, is storage solution the same as pH 4 buffer? The answer is not, no, it's not. But there is a hierarchy that we would recommend in terms of storage solutions in general. So storage solution is a salty, somewhat acidic solution that inhibits bacterial growth and maintains the equilibrium between the salts in both the reference I'm sorry, the electrolytes and the solution. So in the case that storage solution isn't available, then the next option that we would prefer, it would be a pH 4 buffer because it is a salty acidic solution. And if pH 4 buffer is not available, excuse me, pH 7 buffer. And then again, if you don't have pH 7 buffer, I mean, tap water would be preferable before distilled water. And then if you absolutely want to keep it moist, distilled water even isn't that great because it'll dehydrate. It will also pull out the salts from the electrolyte. So, I'm sorry, it'll pull the water into the electrolyte and change the concentration of the salts. So it's really important to do everything that you can to put it into a salty, acidic solution. I'll let you decide. Coca-Cola might even be better than distilled water. How dilute should the hydrochloric acid be for cleaning electrodes? And if acid is used, is a 15 minutes minimum recondition period always recommended? Dilute. They say like 5% hydrochloric acid or less. It depends on what you're trying to clean off of it. I use vinegar successfully for a lot of applications. And when I'm out in the field, if I'm just using vinegar diluted with water, then I do not, well, I don't know if I always hit 15 minutes, but what I'll tend to do, because I have many loggers out there, is I'll grab the pH logger first, download the data, clean it, and then pop it into storage solution while I'm doing everything else. And then the last thing I'll do is calibrate the pH electrode before redeploying. Okay. A question for storage. You said to store it in solution. My probe has a cup with a sponge. Is it keeping it stored in KOH solution the best? So your probe has a cup with a sponge. Yeah, so this is actually an interesting thing that I'm seeing between manufacturers as well, and that is whether you're storing it in a solution or whether you're storing it in a moist environment. And if that's the case, then for instance, your cup with a sponge would be probably the moist environment that I'm reading about. And it's really up to the manufacturer. The goal is to keep your electrode, those inner and outer layers, gel layers, hydrated, as well as the junction. To do that, the best way to do that, I would argue, would be to have it sitting in a storage solution. It is possible as well to have your electrode in a cap that has a wet sponge in it. That would keep it moist too, I guess. But for our products, we recommend soaking it in solution. What do I recommend for storage solution? I've covered what I would recommend if you don't have a storage solution, but I recommend that you use there is actual pH storage solution that is available from manufacturers. Onset offers one, and other manufacturers also offer a specific pH storage solution. It just depends on the manufacturer. So if your electrode is from wherever your electrode's from, I would recommend you contact them to see if they have a storage solution, or you can use anyone's storage solution depending on what that electrode is. If you do store it dry, yes, there is a concern that the electrolyte inside would get dry. So usually, and salty. So usually one that is a person that is going to use a pH electrode stored dry will have a pH electrode that has a removable cap for the internal electrolyte, and then you take out that internal electrolyte, rinse it with some distilled water to rinse it all out, and then you store the electrolyte dry. Thanks, Alex, for attending. Is it okay to deploy the onset sensor with a copper guard in salt water? It most certainly is. As a matter of fact, that's pretty much where we would recommend using that copper guard, because salty water is where you're going to have some biofouling, and the copper guard is really good for that. You do not take in situ water samples to calibrate the MX2501. That's not quite how calibration works with pH. So we do have a conductivity logger where you deploy it and you take an in situ measurement at the beginning of deployment, maybe in the middle of deployment, and then maybe at the end of deployment, and it'll quote unquote calibrate the conductivity readings to that. This is not how our pH electrode works. To calibrate it, we definitely recommend using calibration buffers. Good question, Josh. How does the solution recondition the probe? It does that by rehydrating. It's a really cool dynamic between the internal and external gel layers, and that is they have a specific ion concentration in those tiny, tiny microscopic layers, and the internal electrolyte has a specific salt content, and the storage solution has a specific salt content as well. So what it does is it reconditions those layers to have the right amount of ion concentrations that it's pulling from those salt concentrations. So that's how it reconditions it. Can you correct your measurements for different temperatures? Tom, if you're still out there, I'm not sure what you mean by that. Yeah, I don't know what that means. Does algae growth affect the pH? Yes, it definitely does. So this is going to go back to the importance of your interval for maintenance, and it will depend on your specific application. If the algae is growing in 3 weeks, I would recommend going every 2.5 weeks to prevent the algae from growing and making sure you have good data. Someone asked if we are planning to add other parameters to measure for water. We currently have DO, conductivity, and pH. This person's looking for ORP, turbidity, TDS. We have temp, but for ORP, turbidity, and TDS, we always love hearing some recommendations for the parameters that we should be adding to our portfolio. And it's possible that we are working on some of these things. But right now, no, we do not have those available. How do you avoid biofouling in marine waters, especially fishery operations, on continuous monitoring equipment? Well, that really depends on what you're willing to do. So some manufacturers recommend or have been grandfathered in to be able to use some gross toxic chemicals that are not allowed to be used by pretty much everyone else in the world. Or you could be like one manufacturer and just tape your entire logger or sonde or equipment in copper tape. When I did shark research, we were monitoring shark movements, and with the Vemco receivers, we would cover them in marine, I guess, lube of some type. It was really gross. So, yeah. Okay. Is there any additional recommendation for cleaning or reducing abiotic fouling? Aha, yeah, this is actually a really cool one. So thanks for asking that, Allison. In terms of the fouling, there are two different styles of fouling. One is the biological fouling, and one is the sediment fouling, essentially. So, for instance, with the pH logger that was deployed in acid mine drainage, yes, we were getting iron precipitation. We were getting a bunch of disgusting orange fouling on the electrode. For mitigating that, some manufacturers have brushes. Based off of my discussion about not touching the glass bulb, I'm still wary of the brush thing. Some people are using UV lighting. Some manufacturers using UV lighting. Some people are using nothing. So that's Onset has our copper guard, which does mitigate biofouling. But when it comes down to sedimentation fouling, our recommendation for best practice there is to go out there and clean it as often as you can, or as often as necessary and you can. I know, I wish that were a better answer, but that's sort of what I have now. Okay, let's see. If you've calibrated your probe at representative temp, but your in situ measurements are at a range of temperatures, and you know the temp when you take a pH reading, is there a formula for correcting? Yeah, ultimately in a situation like this, my best recommendation would be something that you probably don't want to hear, but that is to, instead of taking the pH values from your logger, actually taking the potential values from your logger. And, I don't know, that doesn't answer your question, actually. That's a really interesting question. our loggers specifically, mitigate differences in temperature, it's just a good idea to definitely to calibrate at the same temperature that your sample is. If you calibrate to that temperature and you're within, I think, plus or minus 10 degrees Celsius, or actually plus or minus 20 degrees Celsius, maybe, you're still within, it's still acceptable. The calibration is still acceptable. So if you calibrated it at, for instance, 25 degrees Celsius and your sample is 35 degrees Celsius down to 15 degrees Celsius, then that calibration should hold pretty well in terms of accuracy. Let's see. To the temperature question, does the HOBO excuse me, 1 second. Does the HOBO Assistant offer temperature correction of pH measurements like it does for DO? Okay. For the Onset MX2501 pH data logger, it is a Bluetooth pH data logger that communicates with HOBO Mobile. And when you're calibrating, it takes into account the temperature of your calibration solutions, and then the equation or the algorithm that is used to convert your potential and your temperature readings will then therefore be temperature compensated as well. You don't need to do this. It does it for you in the software. So that, I hope, answers your question. The manual recommends calibrating every 7 days, but it sounds like it could be longer between calibrating depending on conditions, correct? Yes, Sean, this is true. We recommend 7 days just out of best practices in general. If you're in a laboratory, oftentimes they will be calibrating it 2 to 3 times a day or at the beginning and end of every shift. So that's because they're looking for incredible accuracy. When we're deploying a pH electrode either on a multiparameter sonde or a data logger for long-term studies, we aren't expecting, hopefully, that it is reading to 0.001 degree of accuracy. So with that in mind, yes, you could probably go longer than 7 days. I have a pH electrode or a pH logger deployed, one of ours. Again, I said in the Quashnet River on Cape Cod, and it held pretty steady for 2 to 3 weeks. I think 3 weeks. The first 3 weeks, I didn't touch it. I just wanted to see what the drift would look like, and it actually didn't drift much at all for the first 3 weeks. The water was starting to get cold. This was late fall, but yeah, it maintained pretty well. So you'll start seeing the drift. It'll be pretty obvious, or you'll see something that looks like drift, and then you'll go and calibrate, and then find out it's maybe not drift, but it's actually your sample. So it's good to keep on top of that and be aware of that. So we do recommend every 7 days, but it is really application specific. Is the use of a central wiper safe for the electrode on a multi-parameter sonde? That is a question that I think is subjective, unfortunately. The manufacturer obviously believes that it is, and that's why they have it, and that's why they recommend it. I've heard issues with the wiper in that it can freeze, and one customer said to me, and you better hope that it doesn't freeze on top of your electrode. Presumably the application for that wiper will be in salt water, and essentially, though it'll be wiping, your electrode could maybe get reconditioned by just sitting in that salt water, but at the same time, you always want to recalibrate after you are reconditioning. So I assume that since it's so widely adopted, it is not causing major errors in the reading. I personally have not used a wiper. I've just talked to a lot of people who have. And I am not by any means recommending you just toss your wiper, because the loggers that have those wipers are not cheap. But I would argue, and I'm hoping that the manufacturer of that logger would argue with me, that in terms of the accuracy that you're looking for, that brush may not affect it so negatively. Okay. Thank you for the questions and for attending. I don't have, oh, there's one more. What is your typical logging interval? Mine currently is at 5-minute interval. The benefit of having a pH logger or multi-parameter sonde as opposed to grab samples is that, first of all, pH is diurnal very often, so you'll be able to see the diurnal changes in the pH of your body of water. But also, if you have an excursion in your pH during the interval between when you went out there for a grab sample, you won't know it happened, and you might miss something important in your environment. So for me, I have it deployed in a river that has a pretty good flow. So I have it every 5 minutes just in case for some reason something happens. I'm actually there. I'm doing a couple of other studies there. So I'm intrigued to see how that pH is being affected by other events. Could you do 1 month plus deployments in a marine setting? You certainly can. I mean, you can have as long as you want for a deployment, but you still need to get out there to maintain it and to calibrate it. If it does get fouled or if it starts to drift, you'll see that, but you'll still have a general idea of what the pH is. So it depends also on what you're looking for. If you're looking for excursions or if you're looking for just a baseline, then that'll affect whether you feel comfortable doing that or not, I think. Okay, well, thank you so much, everyone. I appreciate your attending the webinar. I know there's a lot of theory, but I hope that the second half covered your questions about best practices. I believe very strongly, because I'm a nerdy scientist, that you need to understand the why behind the what to do. So thank you again for attending. Thanks for all of your valuable questions. And yeah, I definitely hope that this helped you out. If you have any other questions, feel free to reach out to us at the links that I provided. You'll also be receiving a copy of the recorded webinar, so you can share this with your teams or rewatch it if needed. And yeah, so thanks very much. Have a great day, everyone, or night.